Francesco. So as usual, feel free to ask as many questions as you want. I will interrupt periodically Francesco. And as you saw from the last lectures, he left plenty of time available for discussion. So don't be shy, ask as many questions as you want. It's good and we all learn something. So Francesco, please, fourth lecture.
Fourth and not last yet. Yes.
And not last yet. Almost there, though.
Yes, almost. Hello, hello everybody, and thank you, Enrico. And as you say precisely, I have material to allow a lot of time for questions. So I will, especially this lecture that has several disconnected topics, I will stop regularly and feel free to ask as many questions as you want. This is the best part of the lectures. It gives me feedback of the fact that you are actually listening and you're actually understanding. You've been asking very good questions, and it's useful to you as well, I hope. So let's continue this way. And today is the fourth lecture. So the last few lectures, we discussed mostly about the thermal production of relics, with a specific focus on cold relics, since hot relics we saw they are excluded. And so today we will continue the discussion that was just anticipated yesterday on experimental searches. So we will discuss the strategies, and we will give more details about these three different strategies to search for cold relics. Let me see. Okay, very good. So here is a summary of the last part of the previous lecture, with also this famous result for the relic density. And this famous result tells you that the cross-section you need to standard model final state is more or less of 1 picobarn, which is the size of processes mediated by weak interactions. And if you want at least the dark matter not to be overproduced, so to have more than you actually observe, then this gives you a lower bound on the cross-section. So you need some minimal interaction strength between the standard model and the WIMPs. So you can read this diagram from the three different ways that we discussed yesterday. You can have annihilations, you can have collider searches, and you can have elastic scattering. And so in this lecture, I will have three different parts, and each part will be devoted to one of these cases. So we begin with the annihilation, which is the same process that sets the freeze-out relic density, but the freeze-out relic density is set by annihilations happening in the early times, okay? Now we are considering WIMP annihilations happening today, and happening not too far away from us because we want to detect them. If the source is too far away, then the flux will be diluted over the solid angle, okay? So for each one of these searches, I put some one reference, which I think is very good. So this is a reference of TASI lectures from 4 years ago on indirect detection. And this is the same kind of figure that we saw yesterday. So I will not repeat myself too much. I just want to emphasize that you can annihilate to any standard model final states, or even beyond the standard model final states, which are usually unstable. And then you have this decay chain, and you have this hadronization process for core or stuff. What you get in the instruments on the Earth and on also satellites are stable standard model particles. So positrons, electrons, neutrinos, protons, antiprotons, and gamma rays. So I could easily teach 4 or 5 lectures only in indirect detection. So since this is just an overview, I want to focus on one example. The one of photons final states, okay? So we will discuss the case when the instrument that we use to detect the flux of this particle is detecting photons. So here is again the figure, and I also put something that I believe I said yesterday. So you could have an annihilation of 2 dark matter particles to standard model final states, or you could have a dark matter decay with a lifetime longer than the age of the universe. From the kinematical point of view, these two processes are identical, because the decay is a decay that happens in the rest frame, and dark matter particles moves very, very slow, with the velocity typically around 10 to the minus 3 in units where the speed of light is 1. So this is a decay basically happening at rest, and this is an annihilation of 2 particles annihilating at rest. So it's like a decay of a big particle with mass twice the mass of a single dark matter particle. So I will discuss both cases and I will make connections among them later on. So I would like to mention that there are good things about photons. I mean, there are good things and bad things about all the possible final states. So since we're focusing on photons, let me tell you that the good thing about photons is that they carry directional and energy information because they propagate without further interaction with the interstellar medium, the intergalactic medium. And for example, if we detect a photon coming from a specific direction, we know that it was produced along that line. The source was on the line along the propagation direction. Same for the energy, they do not lose energy. So if we detect a photon with energy 10 GeV here on Earth, we know it was produced with energy 10 GeV at the production point, which would be this dark matter annihilation, okay? So on the contrary, just to give you one example, so it will be clear the difference. If you have a positron, then the positron is charged, it carries electric charge, so it gets deflected by the galactic magnetic field, and it also loses energy through synchrotron radiation. So you lose directional information, you lose energy information, and in order to reconstruct them, you need to model very precisely the magnetic field of the galaxy, which is something that is very difficult to understand. So at least the photons have these two benefits. Of course, there are also downsides, and one of them is that there are many processes in the sky producing photons, and usually the photons produced through these dark matter annihilations are a subdominant component of the total photon flux. So the challenge here is to discriminate the signal over the background. So what kind of spectra we expect from annihilations? Or again, I emphasize, if you have a decay, you can have the same story, just replace 2 MK here, 1 MK here, but the kinematics is identical. So you see here, I plot the photon spectrum normalized in this way, where X is the photon energy, where the units are set in such a way that energy 1 is equal to the MK. So for the annihilation case, this is the maximum energy that the photon can carry. And you see that if the final states, so the primary annihilation channel are standard model quarks or Ws or Z, the spectrum is quite featureless, means that there is no preferred energy, and you see it's almost constant over a large range of energies. On the other hand, if you have a peculiar spectral shape, such as in the case when you annihilate directly to photons, then in that case, ideally the spectrum would be a delta function, because this is a decay happening basically at rest. But then you have detector resolutions, and you see that the purple lines here are, let me cover the caption so you can read. This is, you see the different delta E over E, where delta E over E is the detector resolution. And you see that there is some spread, okay? There is some spread, but in the case of a line, it's difficult to disentangle the signal from the background, because the signal is something very peculiar, and especially if you look for gamma ray lines with energy around hundreds of GeV, there is no known astrophysical processes giving you monochromatic photons at that energy, okay? So this is a powerful way to find new physics through detecting photons. Okay, so the prediction for the flux is given by this expression here. So we are interested in knowing how many photons we get per unit energy. So you divide by this flux factor, is the area of the sphere, where R is the distance between us and the source. Then this is the function I was plotting here, the function plotting here. So it's, once you have an annihilation with the dark matter mass at rest with energy MK, how many photons you produce per unit energy. So it's really the function plot here up to the normalization, which is different, but it's something that depends only on standard model physics, because the evolution of the final states all the way to give you photons is only governed by standard model interactions. Then this is the number of annihilations, and per unit time, per unit volume, n chi² sigma v. There is a factor of 1/2 because you want to avoid double counting the dark matter particles. Here you're basically summing over all the possible dark matter pairs, okay, that annihilate through each other. Then you have the volume of the region that you are observing, where these photons are produced. Then you have the area of the telescopes and the exposition time, okay? So you can rewrite this equation. I invite you to do the intermediate steps, but it's really straightforward. All I did was to replace n chi with rho chi divided by m chi. So you see there is an m chi square in the denominator, there is a rho chi square here. And you see that there is a nice factorization of the total rate into one contribution that depends only on the detector, one that depends only on the particle physics property of dark matter, so the annihilation cross-section and the mass, one that depends only on, I call it standard model, because as I say, the evolution is entirely controlled by the standard model. And then there is something that depends on the astrophysics. It's the integral over the volume. I went to polar coordinates, and the R square simplified with the integration measure of the dark matter density square. So usually what is detected is the differential flux per unit energy and per unit solid angle, and it's given by this expression in red, where the astrophysics is entirely parameterized by this so-called J factor. And here I specify J an because it stands for annihilations. In the next slide, we will see how things change for decays. And you see that you integrate along the line of sight, okay? The line of sight inside is infinitesimal solid angle element, okay? So this is given a WIMP model, okay? Or dark matter model in general, if you want to know the flux that you detect here, the WIMP properties only comes through this prefactor here. Then there is a function which is known from our study of standard model physics at Collider. And then the astrophysics is inside this J factor here. So if you have decays, the calculation for the photon flux is very similar. There are some changes. So I tell you what you need to change, and then you can try to rederive everything. So the only difference is actually here. When you change from annihilation to decays, you replace this just with one single power, because now you do not have two particles in the initial state, you just have one. And instead of the cross-section, you put the decay width, okay? So it's interesting because the J factor, the factor parameterizing the astrophysics, for decays and for scattering are very different from each other, very different. They are different, okay? In one case, you have the integral of the density square. In the other case, you have the integral of the density to the first power. So as I mentioned at the beginning, photons carry directional information. So this J factor also depends on, it's an integration along the line of sight, but it depends on what direction you're pointing to. So by studying the photon morphology, namely by studying the incoming direction of the photons you detect here, you can in principle distinguish if these photons were created by annihilation or decays because of this different profile, okay, that you expect. So let me discuss now the bounds. I will discuss bounds for weak scale dark matter. Let's have in mind that there is this benchmark value of 3 × 10⁻26. So you see that this is the number that we have in mind from thermal production. And you see here, there is a plot from the Fermi collaboration where there is a plot very similar to the one I showed you yesterday, dark matter mass versus sigma V. The dashed line here, the almost horizontal line, is the thermal cross-section value. And the black line is the excluded region. The excluded region is, of course, the one above, because cross-sections must be smaller than some value. This is the bound, because we haven't observed anything. So this is the case for the specific annihilation to tau final state. So it's a specific, and if you look at this paper from the Fermi collaboration, they give you bounds for all sorts of different standard model annihilation final states. And you see that for the tau case, thermal relics with mass below 100 GeV are actually excluded by Fermi, but of course the bounds depend on the masses. This is a discussion about gamma rays. I would also like to mention X-rays, not just to, I don't want to deviate too much from the main discussion, but they are interesting because the sterile neutrinos, so right-hand neutrinos that are arising in theories providing the neutrino mass, if they have a mass around the kV scale, here there is a precise prediction for the mass density. And remember that 0.1 is the number you want to reproduce, and the angle theta is the mixing angle between the active neutrino and the and the sterile neutrinos. You need the angle because, of course, to go to photons through this loop diagram, you need to mix into an active neutrinos. So the production is a complicated story, can be enhanced by electron asymmetry. What I want to say is that a smoking gun signature of this framework is a line in the X-ray, so around the keV range. And this is the lifetime you expect for the sterile neutrinos. And the decay producing this line is the sterile neutrinos going to an active neutrino plus a photon. And then the energy of the photon is, of course, the half of the neutrino mass in the initial state, because we can neglect the mass of the active neutrino in the final state. So there are also other candidates producing X-ray lines. The sterile neutrinos is a particularly motivated one, so that's why I wanted to mention. And it's interesting because in 2014, there was a discovery of an X-ray line at 3.5 keV, but it's quite controversial, okay? So there is no conclusive evidence because you can see the line in some environment, but you do not see the line in other environments. And also the numbers that you need to produce this line with the neutrinos are not consistent with the relic density. If you plug the relic density here, you see that you don't reproduce this number. You actually need to invoke this mechanism here, but that's actually not a big problem. There are other issues with the 3.5 keV line. There are complementary observations that seem to exclude this, but it's still something that is discussed actively on the archive. So you can find papers regularly, still 6 years after the discovery. The last thing I discuss, and then I will stop for question, is to conclude the topic of indirect detection, and in particular to conclude the topic of probing dark matter annihilations. We can also probe dark matter annihilations happening much longer after the freeze out, so at temperatures way below the dark matter mass, but also much earlier than today. And because these are, of course, out of equilibrium annihilations, so we are way past the freeze out, but these annihilations could deposit energy into the plasma, and in this plasma, you are forming heavy nuclei through BBN, you're forming hydrogen atoms at the time of CMB formation. So you are going to affect the prediction of standard cosmology in the absence of these annihilations. And as we discussed, and as you have seen, especially in the previous week, in the lecture series on cosmology, this is quite a success of the standard cosmological model, the prediction of the light elements. And the same for dark matter decays, of course. The story is identical. If you have decays, they can happen also at these times, and they can produce some distortion of the CMB spectrum and so on. So let's look to quantify these bounds. The best way I know is to show again this plot that I showed you yesterday. And then you impose these bounds here, and the gray region is excluded. Okay, this is excluded for a relic which annihilates to visible final state through an S-wave process. Okay, so the gray region is excluded, and the precise bound actually depends on the specific annihilation channel. So here I took an average, but it doesn't change much by if you consider different states. The line will almost be identical to this one. So you see that thermal relics lighter than 10 GeV are excluded by CMB bounds. That's the origin of what I call the WIMP window yesterday. If you remember, I told you that we took the WIMP window to be between 10 GeV and 100 TeV. 10 GeV was coming precisely from this bound. And of course, here you are assuming S-wave, and you're also assuming one single relic with a constant cross-section. There are many caveats, okay? But in the minimal framework, these relics are excluded by CMB bounds. Okay, so I will stop for question now. Enrico, please.
Yes, very good. So we have several questions. So let me start with the first one from Disha. So Disha is asking about with photons, won't they miss some energy because of Bremsstrahlung and synchrotron radiation?
Okay, so no, this is a good point. That's something that I decided to skip, but when you annihilate to electrons, for example, or to other charged particles, you produce gamma rays from initial state radiation, okay? So this is a photon emission right at the production point. But then the electron propagates in the magnetic field, and it's true, there are also photons coming from the energy loss of this electron. But these are at much lower energy, okay? So the photons I've been talking about have an energy very close to the dark matter mass. If you have something with scale 1 TeV annihilating here, the photons I've been discussing, the one that are predicted by this plot, you see here, you don't go much below the mass. The one coming from this final state, from this synchrotron emission, I have an energy much smaller. And you can look for complementary probes. This is something that I didn't discuss, but it's true. There are also photons coming from these processes here.
Very good. So next question is from Tessio, who's asking, is the deflection by gravitational fields relevant for the photon propagation direction?
In this context, no. In this context, no. They are very energetic photons. They basically propagate straight.
Okay, so next question is from Sudipta, who's asking, normally people take the decay lifetime of the dark matter to be larger than the age of the universe for the stability of the dark matter. But here you're talking about the decay of dark matter. So can you explain more on that?
Yeah, so the dark matter lifetime is given by a number, which is a number much larger than the age of the universe, but it does not mean that there are no decays until that time, okay? The particles are not decaying all together at that given time. There is this exponential decay, and the lifetime tau is so-called the half time. So the number of particles, it will be the total number times e, the exponential, to the minus t over tau, okay? So we are talking here, when we talk about bounds, about the first decays, and a small fraction of dark matter is decays. Most of the dark matter will decay later on at the time very close to the lifetime. But these are the first decays in the exponential profile.
Excellent. So one more question from Sudipta. And so Sudipta is asking, is this the enhancement due to the Sommerfeld enhancement?
No, so I've not been discussing about Sommerfeld enhancement in these things. I've been only taking sigma v equal to a constant. So Sommerfeld enhancement is something that arises when you have a long range interactions, but I'm not covering that.
Okay, so one more from Ankit. In the Fermi-Lat exclusion plot, what type of sigma v and dark matter mass relation is assumed to get a roughly flat thermal cross-section curve?
So in this plot here, this line here is the same as the line here, okay? And this is a line that arises from the numerical solution of the Boltzmann equation, so the one I discussed yesterday. Actually, this is a plot I made with my computer to just derive the relation between m and sigma. So you treat m and sigma v as independent parameters, okay? And then these independent parameters give you a prediction for omega h squared. This line is the line corresponding to omega h squared equal to the observed one.
Okay. One more question from Lucas. What cosmological or astrophysical structures would theoretically be the best targets for indirect searches?
So the best targets are usually at least for gamma rays. For gamma rays, the best targets are the center of the Milky Way, for sure, because it's a very dense region of dark matter and it's not too far away. But of course, the background there is huge and not well understood. So it's good because there is dark matter there and it's not too far away, but it's also bad because the background is a bit of a problem. Then the dwarf galaxies, these are satellite galaxies that are smaller than the Milky Way, are spherical galaxies dominated by dark matter and orbiting around the Milky Way. These are also good targets because they have less background and they're not too far away, okay?
Okay, we have a comment from Anupam, so let me read it to you, then you can comment on top of it. So Anupam is writing, this cosmic photon, I think the photon produced by the annihilation, can produce further electron-positron pairs, and then we can lose the photon.
Yeah, so I mean, what I've been quick here, but when I show you a plot like this is taking basically all of this electromagnetic shower into account, okay? So all of these effects are accounted for when you derive this prediction for the photon. So yes, I mean, you can create E plus E minus pair from photons, then the E plus and E minus can radiate. When you compute the spectrum, you are accounting for all of these effects.
Okay, one more question. I think we can take this one, then we can move on, probably.
Okay.
So again from Sudipta, in the context of sterile neutrino, you have talked about some enhancement from the lepton loop. Is this an enhancement due to the Sommerfeld effect?
No, so this is an effect which has nothing to do with Sommerfeld, and it's not due to loops. It just arises if the lepton asymmetry is larger than the baryon asymmetry. So we know that there is an asymmetry between positron and electrons, because in the current universe we have electrons and not positrons. And the universe is neutral, so the number of electrons must be equal to the number of protons. However, unlike for the baryons, for the leptons, we do not know what is the ratio between neutrinos and antineutrinos. So in principle, the lepton asymmetry can be larger than the 10 to the minus 10 or 10 to the, it depends what variable you use, but you know, the one of baryons. So if this number turns out to be larger, then this production is enhanced through a complicated resonant effect, but it's not the Sommerfeld enhancement.
Okay, excellent. So let me pass you one more question because I think it's related to this part. So this is asking,
let's finish this part. That's good.
So what does box and VIB stand for in the plot?
So box is a box shape when you annihilate to two intermediate final state and each one of them decays to gamma gamma. You know that if the pion, the neutral pion, decays with the non-zero velocity, so not in the rest frame, when you observe this decay in the lab frame, the energy spectrum of the photons is flat. So flat is called, the flat spectrum is called box because it has the shape of a box, okay? It's like a rectangle. And so if you have some object like the neutral pion that the dark matter decays to, and then each one of them decays to two photons, then you have some spectral shape, which again is not a line, but it's something characteristic. VIB is virtual internal Bremsstrahlung, and it's corresponding to the case where the photon is radiated from some internal leg. And in some kinematic region and in some spectrum, for some spectrum of initial state and the virtual state, this has a spectral feature very, very similar to a line. And so that's why they put it here, because it's something you can look for in the cosmic rays on top of the background, which is very smooth.
Okay, there is one more question. Do you want to take it now?
Yes, there is time.
Okay, so from Anupan, how one can be sure if the photon is okay, so how can we confirm that a hard photon is coming from dark matter annihilation?
I don't understand the question, sorry. It's I mean, you have a model for your astrophysical background, and then you are trying to subtract from the data the background, and if you see an excess, you can try to model with the photon, the photon spectrum arising from dark matter annihilations.
So Anupam, if the question was not this one, please reiterate, and later on I will pass the question to Francesco.
Okay.
I think we can move on.
Okay, very good. So we can continue. It's perfect because we spent 30 minutes on the first part. It's great. Keep asking questions. You see the number of slides is almost half. So now we discuss about direct searches. So the reference I suggested are these Stasi lectures from 2009. And you see the sketch of the figure I showed you yesterday. And this is the position of the Earth on the galactic disk. And then there is a WIMP halo. And since the solar system and the Earth with the sun, of course, is spinning around the center of the galaxy, the effect is that there is a WIMP wind. There is a net velocity of wind hitting us on the Earth. And so we are hit by this flux of WIMPs, exactly as the way we are hit by solar neutrinos. And we can try to do something similar that we did in order to detect the solar neutrinos. And we look for scattering, okay? But in this case, the scattering must be elastic scattering. Not always, but I will discuss only elastic scattering. Then there are exceptions, but the conventional way is to look for elastic scattering. So the experimental signature is to have a nuclear target on the Earth in our labs, and you have to be very careful about the background, also about the shielding, because not only WIMPs come toward the Earth, but also cosmic rays come toward the Earth. And so if you go deep underground, such as in the Gran Sasso mountain, then you are shielded from cosmic rays, and then dark matter is what makes it all the way inside the lab. And these experiments are difficult, and the WIMP hit the nuclear target, and then what you observe is the recoil energy. So let's try to estimate the flux. So the local dark matter density, so in the solar system or around the Earth, it's more or less constant. Remember, in the first lecture, I gave you a radial profile of the dark matter density, okay? In the Milky Way, if you evaluate that function at a distance of more or less 8 kiloparsec from the center, you find this number here, which is the local density. And you see it's a very small density, because for each cubic centimeter, which is not the large region of space, but it's not even small, it's something you can visualize with your eyes, okay? 1 cubic centimeter. You have not even a proton, 0.3 GeV, okay? So it is a very small density, but it's much higher than the average, actually. And the flux that you expect is, as usual, number density times velocity. This is a general equation. The velocity, you take this 220 kilometers per second. It's the WIMP wind I've been talking about. And if you want to get the number density, you have to use this information that you have, which is the local dark matter density, and then you have to divide the local by the mass. And when you divide the local by the mass, you get the number density. So number density is something that depends on the specific choice of the mass. And again, I emphasize the reason for this is that we measure rho. We do not measure the number density. We infer the presence of dark matter through gravity. So we measure the mass density. Okay, we are able to infer the mass density, but then the number density depends on how heavy is each particle, okay? And so if you have a mass of 100 GeV, you find this number that I already discussed yesterday, which apparently seems very big, but it's, for example, much, much lower than the solar neutrino flux, okay? So fluxes are really tiny for this kind of experiments. So there is a nice analogy that before I show you equations and rates and exclusion bounds, there is a nice analogy that I like to make when I introduce direct detection for the first time to people who have never seen that. And I'm sure that even though you may not have seen direct detection before, probably you have played, or at least you have seen a pool table. Okay, so this is a pool table. And the goal is to put the red, the ball number 3, in this hole here. So if you are a good player, what you do, you take this and then you hit the white. The white starts moving until the white hits the red. And then the red goes here and the white continues in a way that is consistent with energy and momentum conservation, okay? Neglect the rotational energy for this example, okay? Of course, the billiard balls are also rolling, and it's more complicated, but imagine they're point-like, okay, for this discussion. Now, what is happening inside the labs, for example, at Gran Sasso, is like playing pool, but you play pool with the white ball, the so-called cue ball for the experts on pool. The cue ball is different because, first of all, it's something that you do not put in motion, okay? It's coming from the sky. That's because it's a dark matter particle. We have no control of that. It's the incoming flux that I just estimated. And the other peculiar property of this special cue ball is that it is invisible, so we do not see it arriving. But from the point of view of kinematics, what is happening is identical to a game played on a pool table. So this ball hits the equivalent of the red ball, which is now, it's a xenon nucleus, for example, which is a very common target used in these experiments. And then there is some elastic scattering. And what you see on the Earth, inside the lab, is this xenon nucleus, or equivalent to billiard ball, that is sitting there and then for apparently no reason, it starts moving, okay? And since billiard balls do not start moving for no reason, you infer that it was hit by something, and this something that hit the ball is something you cannot see, it's something invisible, okay? So this is the very rough idea about dark matter direct detection. And now we can be a bit more quantitative. Of course, the experimental observable that you observe is the recoil energy of this nuclear target, but the way you measure the recoil energy, the way you reconstruct the energy is through complicated combination of these different signals. And you can ask me questions if you want, but I'm not sure I will be able to answer. These are very, very sophisticated experiments, and it's really amazing what they're doing. So you can either have electric charge, you can generate phonons in the material, you can have light, like emission of photons inside the detector, and then from this signal you reconstruct the recoil energy, which is the energy and the momentum exchange in this collision here. So far we've been talking about nuclear recoil, but as you may have seen, this is an article on the New York Times from 2 weeks ago. These experiments also look for electron recoil. And there has been very interesting results recently. And as I promised, I will conclude my lecture on the axion tomorrow by reporting this last news and telling you more or less what's going on there, but it's something that is still not completely understood. Okay, so now let's try to be quantitative. So the kinematics of elastic scattering is really simple because it's no relativistic kinematics. So it's something that you could have solved in the first year of university or even in high school, okay? It's just conservation of energy and momentum for a no-relativistic system with very simple relations. So I gave you two homework, one for the kinematics and one for the calculation of the rate. Here I will collect the relevant equations. If you're interested in the derivation of these two important equations, I put two exercises that are guided. As usually there are intermediate results, so you can get to the end by knowing what is the best path to follow, okay? So this is the collision that is happening in dark matter direct detection. You have dark matter particle chi hitting a nucleus N, and then you have in the final state the same two particles, okay? I only consider elastic collisions, although there is also an interesting study of inelastic kinematics, but it's beyond the purpose of this introductory lecture, okay? So the initial nucleus is at rest. So if you call Q the momentum transfer in the collision, the electron recoil energy, sorry, I got ahead of myself. The nuclear recoil energy is Q squared divided by 2mn, because the final state momentum is this, and the initial one is 0. So the final state nuclear momentum is the same as the transfer one. And then you have the non-relativistic dispersion relation relating the recoil energy and the momentum, and mn is the mass of the target nucleus. So the maximum recoil energy, this is the kinematical bound that you will derive if you do problem 1. You see that the maximum recoil energy is given by this expression, where mu chi n is the reduced mass of the system dark matter nucleus, okay, defined in the usual way. So this is something that you will derive in the problem 1. But this is very interesting and very relevant phenomenologically, because it tells you that if you go too slow, and this is relevant because this collision is not relativistic, if you move too slow, then you cannot get recoil energy as high as you want. And this is a serious issue because the detector, of course, has a threshold energy. It cannot detect recoil energy as small as you want. If the signal is too small, the detector will not be able to detect that given signal. So if you have dark matter particles moving too slow, then they may induce a scattering with the nucleus, but it's something that the detector will not be able to see. In particular, you can be quantitative, and this is again something that you will do in the exercise. If you want to produce a given recoil energy, and this given recoil energy must be at least higher than the threshold energy of the detector, otherwise it's useless, the calculation. You're predicting something that you can never observe. You can show from the previous relation that this is straightforward actually from here to here. The minimum, but look at problem 1 if you want the details, but the minimum velocity that the WIMP needs to have to produce a given recoil energy is given by this general expression. It's instructive to see what happens when the dark matter mass is much lower or much larger than the nuclear mass. So the the reduced mass becomes one of the two, the lowest of the system. In particular, the case when the dark matter mass is low is interesting because it shows you that you need a velocity which goes higher and higher as the mass goes lower and lower. And this is interesting because it tells you that at some point these experiments will stop being effective, because if the dark matter mass is too low, the minimum velocity that is required is above the escape velocity of the dark matter in our galaxy. So there are no dark matter particles with that velocity. Okay, so there will be no way to see a signal in these events. So the recoils are actually tiny, as I was mentioning. So here is the equation again. We put numbers for a WIMP. So we take we can take a WIMP of mass 100 GeV. The xenon target has a mass also around 100 GeV, just for this estimate. So we put everything at 100 GeV, even the reduced mass. And you see that this is hundreds of keV. Okay, so there are recoil energy much smaller than the masses of the particles in the game. And so we need detectors with a very low threshold energy. I see that there are a bunch of questions, so maybe this is also a good point where I can stop, Enrico, if there are questions.
Yes, yes, there are quite a few questions. So shall I pass them?
Yeah, so let's have some of them.
Okay, so the first one is from Ankit, who's asking, how are the dark matter halo and velocity distribution parameters measured experimentally?
So experimentally, what we can measure in some sense is we can have an idea of the local density and of the velocity dispersion from hydrostatic equilibrium of the galactic system. But the distribution of the dark matter halo, the density distribution, and the velocity distribution, it's something that we don't know. And actually, that there is a very interesting research direction along these lines where numerical simulations try to extract the dark matter halo distribution. I gave you 3 of them in the first lecture. And also for the velocity distribution, the usual assumption is to take a Maxwell-Boltzmann with the given dispersion velocity, which is the one we infer through the hydrostatic equilibrium, because the halo is stable, but the halo has no interactions. Okay, so the velocity dispersion is what is opposing to gravitational collapse. Okay, so from this kind of equilibrium, we get a feeling of this velocity dispersion, but of course, the precise shape of the distribution is something that we don't know precisely.
Very good. So next question is from Lucas, who's asking, could the gravitational well of the solar system or of the Earth itself lead to a higher local dark matter density? And how sensitive are bounds to these uncertainties in the flux?
So it is possible, and it's actually there are studies of dark matter, especially inside the sun. The sun is a very dense region, and it's bigger than the Earth. And you could trap dark matter inside the sun. This is actually a way to measure the nuclear interaction of WIMPs. Interaction of WIMPs with nuclei by studying how they are trapped in the sun, and then by studying the subsequent annihilation. You create a higher density of dark matter in the sun. But this is something that is not affecting direct detection, and it's not a big uncertainty in the flux. As far as I'm concerned, the only issues can arise for low dark matter masses below the GeV scale. So let's say outside of the WIMP region, and also outside of the region where these nuclear recoil experiments are effective, then you can trap some in the sun. But for the plots I'm going to show you now, this is not a fact to be concerned about.
Okay, so we have a reiteration by Anupam on a question that he asked earlier on about the energy of the photon. So maybe I will keep this for the end of the lecture. And
okay.
go on with questions on.
Yeah, let's continue with the direct detection. So we close.
Then later on, so Anupa, at the end of the lecture, I will ask Francesco again your question. So about direct detection, the next question is from Dibiendu, who's asking direct detection. So xenon 1 ton is sensitive to dark matter particles which are heavier than 1 GeV. If the mass is less than 1 GeV, then how can we detect it directly?
So there is a lot of experiments looking for sub-GeV direct detection by studying electrons as targets. And this is something that I will not have time to mention today because in just one lecture, I want to give overview of these three main strategies. So I'm focusing on the one that is more mature and was the first one historically. But if you want to go below the GeV, you can either, one option is also to, and some experiments are trying to do that, to lower the threshold of your detector. And so you can go to lower masses. But otherwise, you can use the electron recoil where the kinematics is different. And there are lots of experiments searching for sub-GeV direct detection. So there are experiments also. So it's actually a huge effort in the last 10 years.
Very good. So next question is from Sudipta, who's asking how to distinguish between electron recoil and nuclear recoil.
Very good question. So this is very relevant for what I will tell you tomorrow because not all the experiments can do that, but the xenon experiment can, and that's actually how they were able to distinguish the electron recoil events that we've been hearing about in the last 2 weeks. So maybe I will answer this question tomorrow when I will talk about the xenon results. And I will show you maybe a plot from the experiments that basically the short answer is that xenon is sensitive to 2 of these 3 signals. And the way they show up is different from nuclear and for electron recoil. So by measuring a combination of 2 signals, they are able to infer if the combination was generated by electron recoil or nuclear recoil.
Okay, so we have one last question from Lorenzo. So Lorenzo is asking, how are we sure that the dark matter hits the target if it doesn't interact with the standard model, but via gravity?
So, I mean, the question is if the interactions are only gravitational. If the interactions are only gravitational, of course, we see nothing in the experiment. So these experiments are testing the WIM paradigm, according to which there are other interactions beyond the one mediated by gravitational interactions. If you want a successful freeze out, you need something beyond gravity. Otherwise, you see there is this, let me go to the beginning of the lecture. There is this important equation. And if you only have interaction mediated by gravity, this interaction, well, I mean, you don't even thermalize, so this interaction will not hold. But I'm assuming a cross-section between the standard model and the WIMP of the order of 1 picobar, more or less. So if you do not have that, then you are not testing this kind of candidates. So this type of direct detection experiments are testing a specific class of candidates.
Okay, Francesco. So for the moment, there are no further questions.
Very good. So I think I will continue with the direct detection. So we still have plenty of time. So I will finish this part on direct detection, and I encourage you to ask more questions, and we can keep discussing. As usual, I prepare material for less than 1 hour and a half, so we can have lots of interactions. Very good. Okay, so now that we studied the kinematics, we want to study the rate. And there is this general equation. So please take 2 seconds to look at that. There are lots of informations. And you see, this equation is expressing the number of events per unit time and also differential in the recoil energy, which is the observable that we see in the detector. Problem 2 is a guided exercise that will lead you to the derivation of this equation here. Just to introduce something that perhaps was not introduced, NT is the number of targets, rho chi is the local dark matter density, and the velocity distribution of the dark matter is this F. Sorry, here is F chi, they are the same. And the sigma d omega star is the differential cross-section, differential in the solid angle and the omega star is the solid angle in the center of mass frame, okay? So that's what I mean by this. And the derivation involves few intermediate steps, but all of them are quite trivial. So if you're interested in the derivation, you can look at problem 2 and you will find all the solution with the intermediate steps. So now we will use this equation to compare with experimental bounds, because for a given model with a given cross-section, and I will focus here on a specific cross-section, which is the so-called spin-independent cross-section. Spin-independent cross-section is a cross-section generated by some interactions where the scattering between the dark matter particle and all the nucleons inside the nucleus interfere constructively. And so you see here that in the amplitude, you have Z, number of protons, times a number parameterizing FP, the amplitude for the interaction with the proton, and then A minus Z, which is the number of neutrons. A is the total mass, the mass number, it's the total number of nucleons. A minus Z is the number of protons. And Fn is the amplitude for the cross-section with one proton, with a neutron, sorry, up to kinematical factors. Then this F of ER is the so-called form factor. It's a property of the target nucleus, okay? So this is something that depends on the specific target you have in mind. And you see that all the recoil energy, at least for this type of scattering, this type of spin-independent scattering, all the recoil energy dependence enters only through this form factor. So you can write this if you want the full cross-section that you will put in this equation here. And it's, by the way, isotropic in the center of mass frame. So if you want to do, you can do another integration here. You can put this as the value at 0 recoil transfer and then the form factor. And if you have a Lagrange and a macroscopic model, you can compute this Fp and Fn as a function of the couplings of your Lagrange. So now I rewrite the rate for the spin-independent case, again, in a form that is factorized. And again, as we saw for the indirect detection case, you see that there is a coefficient that depends only on the target, the mass of the nucleus times the number of the nucleus, the nuclei in the target, because the more you have, of course, and the more likely it is that you eventually scattering. Then there is the so-called particle physics factor, which is a factor that depends on the dark matter model you have in mind through the mass and the cross-section. The mass, there is also reduced mass with the nucleus, so you have to account for that as well. Then there is a piece that depends only on nuclear physics, exactly as there was a piece in the indirect detection rate that was depending only on the standard model. Okay, the differential photon rate. So here you have a piece that depends only on nuclear physics, and this is a piece that is known from experiments at low energy involving these target nuclei. Okay, so they have nothing to do with the physics of dark matter, but they're very important when you try to predict the rate. And then there is the astrophysical factor proportional to dark matter local density. Of course, you also have F chi, the velocity distribution. And I want to emphasize that the integration over the relative velocity between the dark matter and the target is not from 0 to infinity, but since this is a differential rate in ER, you integrate from the minimum velocity that you need to produce that given recoil energy. This is the equation I showed you before, if you remember. And then the escape velocity of the WIMPs in our galaxy, because basically this function is cut off to 0 above this escape velocity. Okay, there cannot be trapped WIMPs gravitation in the galaxy. Okay, so finally we get to the results. And again, you see that this is the WIMP nucleon spin independent. Okay, so this is the bound for the case of spin independent cross section, and you see that it says WIMP nucleon, so it is rescaled. So it's this cross section here with the nucleus rescaled by the number of nucleons. So you get the one with a single nucleus. And in the case where these two number fp and fn are equal, then you can just divide by a square and you get that, okay? Times a mass factor, but these are known factors, okay? So you see that the bound is this black line. And you see that these searches are mostly efficient for a mass around 30, 40 GeV. You see that this line becomes vertical. The reason why it becomes vertical is that if the mass of the WIMP, let's look at the equation again. So if the mass of the WIMP goes to a very small value here, then the minimum velocity grows like 1 over m chi. There is a square root m chi squared, so it's 1 over m chi. So as you go to lower mass, the minimum velocity that you need in order to have a scattering goes to a larger and larger value, and eventually it becomes equal to the escape velocity. So this integral basically has no support, okay? So you get 0 events. So that's why they lose power at small masses. At large masses, there is no bound because, again, let's look at the equation. When the WIMP mass is much larger than the nuclear target, the minimum velocity is a constant, okay? I mean, it depends on the recoil energy, but it doesn't depend on the dark matter mass anymore. So there is no, let's say, there is no penalty to pay for having a large WIMP mass from the point of view of kinematics. There is a penalty to pay from this 1 over m factor. You see, the rate becomes smaller and smaller if the mass gets higher and higher. And the reason is that the flux is getting smaller because the flux is proportional to n, but n is rho over m, and rho is fixed, m is not. So if rho is fixed and m grows bigger, then n goes smaller. Okay, so that's precisely the reason why this line is growing up. So here it's a plot that I took from a few years ago, but it can show you the future projection for this effort. This is the line of xenon 1 ton that at the time was still a projection, but now it's an actual experimental bound. And you see that in, roughly speaking, 10 years, there will be the Darwin experiment that will reach the sensitivity able to touch this orange line, and this orange line is the so-called neutrino floor, and the neutrino floor is basically the point where you have a background from neutrinos for that values of the cross-section, which is indistinguishable from the signal. And so at that point, you need to come up with some other idea. So this is the natural ending point of direct detection, at least the way I've been discussing today, which is the original way of doing that. Okay, so I think I can stop here, Enrico, because this is the end of direct detection, and then
yeah, we have a few questions.
Very good. Yeah, I mean the collider part is much shorter. It's much shorter. So not because it's less important, but I will explain why. But please let's have more questions because there is plenty of time.
Yes. So the first one is from Dibiendo, who's asking, what is the heaviest dark matter mass that can be detected by direct detection?
Yeah, so in some sense, I kind of answered from this plot. So you see that in principle, there is no upper bound, but of course, this line you should imagine it will continue, okay? In this log axis, it will be a straight line precisely with this slope. And so you can test mass even larger than this TV value that you see here, but then the bounds will become not very interesting because they grow with the mass.
So one more question from Sudipta. So the question is, why the direct detection is giving stringent bounds for a particular dark matter mass of around 33 GeV? I
mean, the 33, I don't think there is any magic about the number 33. It's just that, you know, you have that at large masses, they lose efficiency because of this flux factor. At small masses, they lose efficiency because of this kinematical threshold. And so there is a minimum, and this minimum happens to be around this value. But the number 33, I don't think it's just, you know, they are bad here, they are bad here, they must be good in between.
Okay, so a question from Ankit. Will you briefly talk about the dark matter annual modulation and maybe DAMA results?
So no, I will not talk about it, but I can say something. So let's look at this picture. Actually, this is not a very good picture, but you know, the WIMP wind is the WIMP velocity that hits the solar system, okay? And it's 220 kilometers per second. The Earth is moving around the sun, okay? So imagine that there is the sun, there is a constant vector, which is the WIMP wind, and the Earth orbits around the sun, and the orbit can be taken approximately to be circular, okay, for this discussion, for this qualitative discussion. So it is clear that at some point, the Earth velocity in the sun rest frame will be parallel to the WIMP wind, and 6 months later, it will be opposite to the WIMP wind, okay? So when the dark matter velocity is parallel and with the same direction, the flux of WIMP is minimal because we are moving away from the WIMP wind, okay? When we are moving against the WIMP wind, of course, the flux will be maximum. So this translates into an annual modulation of the signal that you should expect as a consequence of the motion of the Earth around the sun, okay? And there are experiments such as DAMA, but not only DAMA, which are attempting to detect this modulation signal, and so they do not reject any background, okay? They take all the events, and they argue that if the signal is coming actually from dark matter, you should expect to see more when the two velocities are opposite to each other and less when they are aligned. So this is what DAMA has been seeing for many, many years. I remember I was an undergraduate student in Pisa. Rico, I was an undergraduate student in Pisa.
Yes,
and,
yes, we were.
And
we were undergrad, yes.
They were already discussing about DAMA, so it's been a while. And what they say about DAMA well, what they say, people from DAMA collaboration, is that they found evidence for dark matter because they found this modulation. Now, there is an unfortunate coincidence, and the coincidence is that the peak of this WIMP flux is expected to be around the beginning of June. So the peak of the signal is also aligned with our seasons. So it's very close to the beginning of the summer. And so you may imagine that there are also seasonal background here on the Earth that will give an effect that it's the one you would expect from the experiment. So to my understanding, there is no conclusion. Of course, there are other experiments with different targets that they try to test the region favored by the DAMA data, and they excluded the DAMA signal. Okay, so the DAMA signal is in intention to be mild, but I think it's actually excluded from other experiments by a lot by now. But of course, the ideal thing would be to do an experiment with the same detector. And I think there are proposals, I don't know about the status, but to do DAMA in the southern hemisphere, because there the seasons are opposite. So if you have something that peaks in the summer, then you go to do the experiment when our summer is the winter, okay? So that could be a way to, but I think it's fair to mention that several other experiments tested the mass and cross-section region that are favored by DAMA, and they did not find anything. So there is a strong tension between the DAMA result and the one from other experiments.
Okay, so next question is from Sanket, who's asking, can you explain again the first direct detection plot? More specifically, which curves indicate the parameter space sensitivity and which ones indicate the constraints and bounds?
This one.
Yes.
So this one, actually, they're all constraints. There are constraints from different experiments. There is Lux, there is Panda X, and there is Xenon 1 ton. Oh, sorry, the blue, the green and the yellow, this is this Brazilian plot, you know, that gives you the expected exclusion region. And then the solid black line is the actual exclusion region. So you have to be below this black line if you want to be consistent with the data. You have to be below because the cross-section has to be below some given value.
One more question from Sudipta. So the question is, why is spin-independent cross-section smaller than the spin, sorry, why is spin-dependent cross-section smaller than the spin-independent one?
So the reason is that in the spin-independent cross-section, you scatter off the entire nucleus. There is a constructive interference among all the nucleons. And so you see in the simplest case where Fp is equal to Fn, it's the so-called isospin conserving. This is Z plus A minus Z. So you get the Na square enhancement with respect to the cross-section with only one nucleon. And this A square is a huge number because the xenon has an A of 138. I mean, let's say more or less 100, okay? So it's 10 to the 4 enhancement with respect to the spin-dependent case where you don't have this enhancement. So that's the reason. It's constructive interference among all the nucleons.
Okay, so we have one more question from Lorenzo. I think you already answered, but maybe it's best if you reiterate. Can you explain what are the allowed and excluded region in the plot for dark matter direct detection?
Yeah, so the allowed region is below the black line because if you want to be consistent with the fact that you have seen no evidence, then the cross-section must be below some given value. If you go to a region where the cross-section is large, of course, you expect to see something.
So Sudipta is asking, is there an experiment that can put bounds on dark matter with masses less than GeV?
Yes, yes. So I think I answered that before. There are experiments with electron recoils that are more sensitive to the sub-GeV region. And unfortunately, I will not be discussing about them because since this is the first introduction to dark matter, I wanted to focus on the first attempts to do direct detection, which is with nuclear recoil. But I will mention, I'm forced to mention the electron recoil tomorrow because of what's going on with xenon. So I will say something about that. Unfortunately, not about dark matter with the mass less than the GeV. I will discuss about the solar axion interpretation. But, you know, electron recoil is a way to look at something lighter than a GeV.
Then we have a comment from Ankit, who I think is referring to the annual modulation. He's pointing out that SABR, the SABR experiment, is planned in Australia, and they are supposed to run DAMA and SABR at the same time. I have no idea if the correct pronunciation is SABR.
Yeah, I mean, I'm not sure about the time scale, but yes, I'm aware that there is an experiment in Australia that is okay, about to happen.
And Lucas is also pointing out that cosine 100 is also
the experiment. Okay.
Yes.
Okay, good. Yes. Thank you for your comments.
Okay, so I think for the moment that's it.
Okay, fantastic. So we have 20 minutes. So okay. So now I will discuss the last topic about dark matter searches at Collider, and I suggest this nice review written by two experimentalists, Antonio Bovei and Caterina Doglioni, a couple of years ago, where they give you an overview about searches of dark matter with a particular focus at the LHC. So here is the picture of the LHC tunnel. And this figure, I think it's important to clarify what's going on at the collider. So at the particle collider, you have a so-called beam axis. For example, let's discuss the LHC for concreteness, but you know, there has been experimental results on dark matter searches also for LEP. LEP was an E plus E minus collider. So you have this beam axis, this Z axis in this coordinate frame where you have the two protons colliding against each other. And you can define a transverse plane, XY plane. The transverse plane is just the plane orthogonal to the beam axis, okay? So you have your reference coordinate system. Now, when you collide, especially when you collide protons, what happens is that the collision is the collision exchanging a large amount of momentum is among partons inside the protons, which are either quarks or gluons. And so these partons only carry a fraction of the total momentum of the proton. So if you are observing the collision, if your detector is placed in a situation where the two protons are colliding against each other with equal and opposite momenta, okay, so you are in the center of mass of the two protons, this is likely not to be the same as the center of mass of the partonic collision, because maybe the parton coming from the proton on the right here carries a bit more momentum than the one coming from the left, a larger fraction, okay, so it's boosted in this direction. So this is to say that the momentum along the z-axis is not something very useful because you don't know what it was in the initial state collision, but the momentum projected in the transverse plane, so both components x and y, it's something that was 0 in the initial collision, in the initial state collision. So which brings me to the important point that if you collide proton and protons, in the final state, the momentum must be conserved in the transverse plane. This is important because from the point of view of the collider, of the detector, dark matter particles behave exactly as neutrinos. They pass through the detector without leaving any trace, so you do not see them. All you can do is to infer their existence through an apparent imbalance between energy and momentum, okay? And for the reasons that I've just mentioned, you can do this, you can make this statement only for the momentum in the transverse plane, okay? So that's what is basically done at the LAC. So here there is a nice picture from the Atlas collaboration. I have another one from the CMS, just to be fair in the next one. So this is a view of the transverse plane. So you have to imagine the beam axis entering your screen. And then you see that you produce in these collisions 4 particles. The orange one are visible. At this moment, you don't care what they are. They could be photons, jets, but they're visible. And the dashed lines are a pair of dark matter particles that are invisible. You see from this equation, if each arrow is proportional to the momentum, transfer momentum, so this is the projection of the momentum on the transverse plane, you see that the momentum is conserved. These are just 4 arrows pointing at different directions, the 4 different directions in the plane. So the momentum is clearly conserved, but what you see in the detector is actually only these 2 particles. So there is a missing transfer momentum that you can infer from momentum conservation, which is this arrow here, which is just the sum of these 2, the vector sum of these 2, okay? So now there is a picture from the CMS. This is an actual event where you have a jet with a large PT. PT is the projection of the transfer momentum, sorry, projection momentum on the transverse plane. And so you have a PT which is missing in this direction here. Okay, so you reconstruct this event. So bottom line is that if you want to infer the presence of dark matter at colliders, you need to look for an apparent imbalance of energy and momentum. Of course, energy and momentum are conserved. So the reason why you see an apparent violation is that you produce something invisible. So a very standard way to search for invisible particle at the Large Hadron Collider is through the so-called mono-X searches. This is the typical topology of a mono-X search. You have 2 standard model particles in initial state. 1 standard model particle radiates something. I will show one example later. And then you produce the MBM. So what you see in the end is only this state here. And if this state is a photon, this is known as monophoton event. If it's a jet, it's called monojet, but there are also mono W, mono Z, mono Higgs, and so on, okay? So let me show you one example of a monojet search. You have this type of theory where you have a vector mediator between the quarks and the dark matter coupled with an axial current. So you have the mass of chi and the mass of the, here is called V, but I call it A here, they are the same particles. These are parameters of the theory as well as the couplings, G chi and GQ. In this plot, you fix GQ and G chi, and as a function of the masses of V and of chi, V and A, I repeat, are the same, you put bounds from the study of events like this, where you have an initial gluon radiated from the incoming quark or anti-quark in the partonic collision. So you see that what you produce in the final state is only a jet because these 2 particles are invisible, and you get a bound like this, okay? just to conclude this overview, and I'm only showing you an overview because, you know, unlike the case for direct detection or indirect detection, if you want to write down equations for the rates and for particle production, you have to deal with the initial state that is a hadron, and so you have to run some code that will allow you to simulate all the events. So I cannot give you a homework in such a nice way as I did for the direct detection. So I just want to give you a rough idea, and then you can read the LAC papers, and you can at least you know what the basic idea is, okay? So another framework that is usually tested at the LAC is the one where you have cascade decays. So you have two protons producing some heavier partner. So this is known as the stop in supersymmetry. These are stop, but all you need to know is that it carries color interaction. So he has a stronger cross-section, but this is unstable, and it decays through, this is one example of a decay chain, but it doesn't have to be the case. It decays to a final state with a dark matter particle. So you have missing energy in this type of events, but you do not produce the dark matter in the partonic collision as you do for the mono X searches. Here you take advantage of the fact that there are other partners, and again, this happens in frameworks such as supersymmetry, but you don't need to involve. You can also write down a simple model with these states and study the phenomenology of the model. And you have a larger cross-section here because this is a UCD process. The dark matter particles do not have strong interaction. So this is another type of events that you can study. And the final state, of course, here you have to reconstruct the Z, the top, depending on the model you have, but you have also missing energy, okay? So that's an important signature even in this framework. The last thing I want to say is that there is a way to test invisible particles at the collider by studying very precisely the decay width of non-standard model particles. So these psi, the most famous cases are the Z boson and the Higgs boson. So if the decay of a dark matter particle, the decay of this standard model particle to two dark matter particles is kinematically allowed. So let's take the example of the Z boson. The Z boson has a mass of more or less 91 GeV. So the dark matter mass cannot be above, let's say, 45, 46 GeV, okay? 45.5, 0.6. So if it's below 45 GeV, then this process is kinematically allowed. And if the dark matter couples to the Z boson, this branching ratio is severely constrained because we measure the invisible width of the Z boson very precisely at LEP. And we know that it's consistent with only 3 neutrinos to a very high precision. So the coupling must be very small in order to give a small branching ratio. The study of the invisible decay width of the Higgs has not reached the precision of the one of the Z boson, but it's something that may happen at the future Lepton collider, for example. Okay, so that's an interesting direction to follow in the future. Okay, so that's all I wanted to say for the accelerator and the collider in general. As I say, I just wanted to give you a rough idea, and unfortunately, it's not possible to give you nice and simple equations for the rate as I did before. But let me stress again that let me summarize the content of these 2.5 lectures. So in the second part of the second lecture and in the full third lecture, we discussed this cold relics paradigm. I mean, it's a very successful paradigm because it provides you a compelling way to produce dark matter, and it also provides a motivation for this particle through the hierarchy problem of the standard model. So this was a strong motivation to push the experimental program to search for this particle, and the searches for these particles have dominated the scene for the last decades. Things are changing because these particles have not shown up in all of these search strategies. So I just wanted to give you an introduction, which is, I think, is very important for historical reasons, to talk about cold relics, to describe all of these experimental strategies if you are approaching the field for the first time, as I'm assuming most of you are. But the last purpose of these lectures is to convince you that cold relics must be the answer. Okay, I just presented you one option, which gives you a nice way for particle production in the real universe. It gives you multiple ways to be tested at the experiments. So all of this is very nice, but of course, in the end, the experiments will tell you if this is true or not myself, okay? But I believe it's important to know this. And as I mentioned, the lack of positive results from these experiments, by positive, I mean the lack of a detection, and having all the exclusion bounds have convinced people, especially in the last 10 years, to explore drastically different scenarios in the early universe, as well as new experimental strategies. And this is something very interesting that is happening right now. Okay, so I will tell you tomorrow about another candidate, very different from the WIMP, that is the QCD axion. And that's also not a very recent idea. It was suggested in the late 70s. But unlike the case for the WIMPs, the field of axion searches and axion detection has been expanding a lot in the last 10 years, also probably as a response from the lack of WIMP detection. And that will conclude the set of my 5 lectures. But again, this is an introductory course, so I focus on the motivated candidates and the standard searches, but I don't want you to get the feeling that the answer must be looked for necessarily within this framework. You have to be as open-minded as possible, and then the experiments will tell you if you're right or wrong. So Enrico, I will stop here, and we have still some time for questions in case there are.
Yes, so let me start with a question from Lorenzo, who's asking, is that image from CMS a hint for dark matter which has been investigated deeper?
No, I think, well, I honestly, I'm not 100% sure, but no, I think it's just an event that could easily fit within the standard model background. By the way, there are processes mediated by standard model where you have a single jet plus missing energy without any new exotic particle. I can give you one example. If this is a quark and anti-quark, and this is a gluon, then you have a Z boson decaying to neutrino, antineutrino. What you see is a jet plus missing energy, and that's all in standard model physics. So the fact that you see a monojet event does not mean you have discovered new physics. Again, here there is a background, and you have to subtract the signal from the background and see if you find an excess.
So next question is exactly about this. So Sanket was asking, how do we know that the missing energy is dark matter and not neutrinos or any other weakly interacting particle from million other models?
Okay, so the neutrino answer I answer. So if the missing energy is coming from standard model processes, that's something that in principle we know how to compute. Okay, so we collect a number of events, and that's a prediction for the rate. Sorry, we collect a rate, we collect a number of events. But then at some point, you can also compare that with the theoretical expectation for the standard model. And if you see a difference, then it's something beyond the standard model. Then the other million other models, I mean, that's, I'm just saying you can argue that that is something new that is not within the framework of the standard model. It may not be the dark matter, this is true. It can only be something that is weakly coupled, invisible, but maybe doesn't have a cosmic abundance. That's something you cannot establish at collider. Ideally, you would like to discover dark matter in more than one experiment, then cross-correlate the signals. So if the question is, how can we sure that what you produce at collider is filling the dark matter halo? We don't know that, okay?
So we have 2 questions from Disha. So the first one is the following. So neutrinos interact with matter, perhaps with more strength than dark matter. Then why is the neutrino cross-section so low in direct detection? Also, their flux is larger.
So I'm not sure I understand.
I think he's asking why the neutrino floor is down there.
Oh, why the neutrino floor is down there? I mean, that's, I don't think it's, 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 I mean I mean, that arises from, I mean, these neutrinos, okay, these neutrinos are really, for example, the one coming from the sun, they really have a low energy, okay? So this is something that should impact the cross-section, because the cross-section is suppressed for low energy neutrino. And keep also in mind that you are looking for an elastic scattering. The way we usually discover neutrinos is through a charge current interaction, so neutrino convert into an electron, for example. So if you take the neutrino solo energetic and you compute the cross-section for an elastic scattering, that is what you get from the neutrino floor.
Yes. So the second question is, which is related, but the other way around. Can we see dark matter in neutrino experiments, neutrino detectors?
Yes, there are a lot of proposals to use neutrino detectors also to probe dark sectors, but if I remember correctly, you probe I mean, lighter masses. That's also a way to probe something below the GeV, to use neutrino detectors. But WIMP mass particles and neutrino detectors, I don't think so.
So one more question from Manoush. So the question is, how much does the NFW profile for dark matter depend upon the type of interactions of the dark matter particle and upon what those particles are?
So the NFW arises from numerical simulation where you assume that dark matter is made of n-body and no interactions beyond gravity, okay? So it depends on the interactions in the sense that you derive that by assuming no other interaction beyond gravity. And there are studies that are trying to incorporate the dark matter self-interactions as well as the feedback from baryons, and they find something different. So of course, there is a strong assumption when you do the NFW, which may not be correct.
Okay, so let me go back to a question that we left behind earlier from Anupan. So Anupan was asking, how do we know the photon which has energy of the order of mK coming from the annihilation processes? I guess what he's saying is that you measure some photons. So how do we know that we have some photon? With
we don't. Of course, it's again the usual story. You have an astrophysical background that is something that you can try to estimate, and then you detect photons, and then you take the difference, and then you see if what you detect is more than what you expect. But by the time you receive a single photon, you cannot establish if that was produced, if that's just a photon. You don't know if it was produced in... So the game to play here is to try to disentangle the astrophysical background and the signal. Enrico?
Sorry, I forgot to turn on. So there appear to be no further questions. It's 2:30 sharp.
Fantastic. So
I think
we can continue to tonight, I mean this afternoon in the...
Yes, so thank you very much once more for the very nice lecture. I think also the students are enjoying it. There are a lot of questions, so guys, please keep asking. It's very interesting. If you have more questions, remember that we have the Slack channel, and this afternoon in Brazilian time, we're going to have one more Q&A session with Francesco. So thank you very much, Francesco. See you later.
Thank you, Enrico. See you later. Bye-bye.
Bye-bye.